Okay, section 8.2, titled Rational Functions and Their Graphs. We're going to definitely deal more with these rational or polynomial style expressions. We want to be able to identify, evaluate rational functions. You can see we're going to graph them, find domains, asymptotes, and identify any holes in the graphs. So let's get started. A couple definitions to start with. Rational expressions is nothing more than the quotient of two polynomials. So when we looked at our polynomials, you might have a binomial look on top, x plus 2 over the quantity x squared plus 5x plus 7. Both numerator and denominator contain polynomials. That's what we're calling a rational expression. This function would now contain a rational expression, and it would be something that we could then graph. So if we said f of x equals, and so we could just turn it to f of x equals, which we know means y equals. Okay, and we should be able to talk about the characteristics of that graph. Now, I have the example of x plus 3 over x squared minus 16. All the factoring we've been doing is definitely going to be helpful in this section. So if you have a function, whatever it is, you know when you have that function, 1 over that x value they have here is undefined when x equals 0. So in other words, we've always said what you have to worry about is the denominator. So your denominator can never be 0 because we can never divide by 0. The domain is all reals except for those values that make the denominator 0. So we'd say we can graph every single possible number with the exception of whatever makes the denominator 0. Real numbers for which a rational function is not defined are called the excluded values. So another key piece, vocabulary to keep in mind, watch for indirections. All right, looking at our example here, move this up a little. It says find the domain of the function h of x. So right away you start looking at them. They're trinomials. So we said it really only matters or depends upon the denominator. So let's take that denominator. Let's try to factor it. And it looks like what multiplies to give me negative 36. That adds to give me negative 9. X and x in the first slots. And I believe we're looking at a negative 12 and a plus 3. But you try your different combinations. That looks like it works. Foil it out. We'd get a negative 12x on the insides. We'd get a 3x on the outside for a total of negative 9x. Last times last would give us our negative 36. So according to the definition, whatever makes the denominator 0, so we've got it factored. It's easier to see our zeros. We don't have to go to a grapher, do synthetic or anything like we did last chapter. So we can say right now, x cannot equal our 12 from the first parenthesis and our negative 3 from the second parenthesis. So that would be our zeros. Those would be our x-intercepts. But if they are, they will make the graph have these excluded values. And we can't have zeros in the denominator. So if you would now graph this, and you'd be only graphing the denominator, you could see that, yes, that graph would have excluded values. It would cross the x-axis, x-intercept points at 12 and negative 3, and that would not be good because we cannot have zeros when we have a denominator here. Now, even if you graph the whole entire function, so h of x, the numerator is the trinomial and the denominator is the trinomial, if you graph both of those together as a fractional situation, you still should not be able to have 12 and negative 3 because you should see x-intercepts at those 2 points on your graph. That's what you're looking for when you graph. Okay? So what makes the denominator 0 are called excluded values. They would make the equation bad. We can't have that. We can't have zeros in the denominator. All right, moving on. We said we also wanted to look at vertical and horizontal asymptotes. Remember, an asymptote by definition was a place on your graph where your graph appears to approach but never crosses, never touches. And so that means obviously we could have some vertical asymptotes, and all vertical lines are x equals a number, so it might be x equals 3, x equals -2. And the horizontal asymptotes would be our y equals a number equation, and it would be a horizontal line. So we're going to look at both of them. So definition says if we have the factor x minus a, so we've been dealing with that in our last couple sections, if x minus a is a factor of the denominator of this rational function, but not a factor of the numerator, then x equals a, that zero value, that root, is a vertical asymptote for the graph of this function. So it says on this one, identify all vertical asymptotes of the graph of r of x, and you can see r of x sitting here. So you want to definitely try to factor the numerator and the denominator. And we look at the numerator, 3x, there's nothing really we can do there, but we can factor the denominator. So let's do that now. And we got an x and an x. What multiplies to give me a 2 that adds to give me a -3? Looks like that would be a -2 and a -1. So my factors are x minus 2 and x minus 1. They are not in the numerator, so they're only in the denominator. And that's what it says. If it's a factor of the denominator but not a factor of the numerator, then those x values, or those zero values that we used to get, would be our asymptote. So we could say x equals 2 is a vertical asymptote from that statement, and x equals 1 is a vertical asymptote from that factor. And we'd be good to go. So let's just double check. Now obviously you would graph the equation, but we're not there. We're just identifying the vertical asymptotes. So because x minus 2 and x minus 1 were not also factors in the numerator, we're able to say they are our asymptotes. So they should be, when we graph this, where our graph appears to approach but never crosses, never touches. And x equals 2 and x equals 1 is a fairly skinny range, but that's okay. Next, it says write a rational function of the form r of x equals 1 over p. So we know we need a numerator of 1 that has the vertical asymptotes of -2, 0, and 2. So there's a little variety you can do, but not a ton because of what we were given here. So let's go with the general statement r of x has to equal 1 over. Now they gave us the numerator, so that means none of these are going to be factors, so we can immediately go to writing their zero statements, their factors. So when I have an x equals -2, I'd be writing x plus 2. When I have a factor of x equals 0, I'd be putting an x out in front, or possibly even something else. We'll talk about that in a second. And x equals 2 would be a factor of x minus 2. So somebody says, well, couldn't I have some other numbers or other factors here? Then you would have other vertical asymptotes too. If you, for example, wanted to put in x plus 4 down there, another factor, then that would mean we would also have a further asymptote. We don't want that based on they only gave us 3 here. However, this x that we put out front might be able to have a 2 added to it. 2x, that's not going to change anything. That's still going to give me my 0. It's still going to give me my -2, and it's still going to give me my +2. So the key is what you put right here really could vary, and that's really the only variance in this equation. Somebody says, well, what about an x squared? X squared equals 0 would still give me 0. So you have a few options, but this x plus 2 has to be there, this x minus 2 has to be there. So really, your options are right here. As long as that comes out to be a 0 and not any other values, then you're fine. Okay? So there would be some options, a variety, a sample of correct answers. So that'd be vertical asymptotes. So now, as you can see, let's go to horizontal. When you have horizontal asymptotes, you have a three-way process, and you just have to remember the three choices. Horizontal is left to right, we know, and it's going to be y equals. But we're saying up here that our polynomial, r of x, will equal p over q, which is our rational function, where p and q are actually the polynomials. Okay? Now, p is a polynomial, q is a polynomial, they will have degrees. So notice, in each of these, if the degree of the top is less than the degree of the bottom, if the degrees are equal on the top and the bottom, and if the degree of the top is greater than the degree of the bottom. So we've done all three possibilities. So let's go back up to the first one. If the polynomial on top is smaller degree than the degree of the bottom one, then we're just going to get y equals 0. Plain and simple. Okay? Which is your x-axis. If the degrees on the top and the bottom of the two polynomials equal each other, then we're going to take the leading coefficients and we're going to write y equals a divided by b. And yes, if the leading coefficients are negative, you would take the negative sign as well. So if they're equal, you're going to use the coefficients. Y equals top divided by the bottom's coefficient. And the last possibility, if the degree on the top is greater than the bottom, then we can say we have no horizontal asymptotes. All right? With that in mind, let's go to the example I have here. R of x equals, you're starting to look at the polynomials that you were given, and it says identify all vertical and horizontal asymptotes. So let's do the vertical, which was from the last slide again. So we need to factor the denominator, so we will. Probably green would not be the best color here. Let's go a little darker. And we would get an x and an x. And what multiplies to give me negative 20, that adds to give me a positive 1. Looks like a 5 and a negative 4, does it? So there's our factoring. So we have to factor to get the vertical ones. And since none of those factors are up in the numerator either, we're able to say that we have vertical asymptotes of those factors, those zeros. So we would say x equals negative 5, and we would say x equals 4. Okay? Now the horizontal, from this page, we say we need to look at the degree. Looks like the degree of the top term is a 3. The degree of the bottom term is a 2. That means the top is bigger than the bottom, which means we have no asymptotes, no horizontal. I've got it written that way, so no horizontal asymptotes. Okay? And you can, if you're doing this separately, check your work. All right. Moving on. So after we know how to find vertical and horizontal asymptotes, the next step we need to do is let's go ahead and see what it looks like with the graph included. So this one says, using asymptotes to graph. Write the equations for all asymptotes, then graph them as dashed lines on your graph, as well as graphing the rational function. So first of all, let's go through our processes, and I just like to write, vertical, horizontal, because that's what they said. If you want to go vertical asymptotes, horizontal asymptotes, something so that we can identify them, because we don't want to have to guess. Yes, you should be able to tell them by x equals and y equals, but sometimes they look like zeros and other things. So here we go, back to the vertical. Our definition again was factors of the denominator that are not in the numerator. And we look, and we really don't have any factoring to do, so we got an x plus 4 in the denominator. It is not part of the numerator, so we want to say that our vertical asymptote would be x equals negative 4, the 0 that we just got. Now, horizontal asymptotes, start looking. The degree on top is a 1, the degree on the bottom is a 1. So this is where the degrees were equal, which means we need to use the leading coefficients. So we're going to get y equals, the leading coefficient of the top is a 2, the leading coefficient of the bottom is a 1, so y equals 2. So let's go over to our graph first, and let's assume this is by ones. So here's my x-axis, here's my y-axis. Assuming it's by 1, we want all asymptotes as dashed lines on your graph. So if we do dashed lines, and we do x equals -4, we're going to go over to -4, and we are going to draw, oops, I'm in white, that's not helping. Let's undo that. And let's make it blue here. And again, let's go to -4 and draw a dashed line that represents our vertical asymptote. Then let's go to our horizontal, which was a +2, 1, 2, and do the same thing. Okay. Then from there, it's up to you to go ahead, pick up your grapher, put your equation in, y equals, clear all your old stuff out, and you'll probably want to put this in as with parentheses so you get everything handled. So parenthesis 2x minus 1, close the parenthesis, then divided by, open a new parenthesis for the bottom, x plus 4, because they are quantities. Okay, so a little parenthesis work. We've got our equation. So you could then graph some points, but what you're seeing is that we have this asymptote. You're seeing a curve. Let's go a different color. Let's go green for graphing. And we're going our regular lines now. So we're seeing a curve in here. And we're seeing a curve that comes close to this axis, never crosses, never touches, and one here. Now, yes, it would be good to go to your table, get some of the points that are there. They probably will be messy. It depends on what values you're using. So like, for example, at 0, it's -0.25, so a quarter. At 1/2, it's 0. So you're going to be able to get some points off of this. 1, it's 0.2. So your asymptotes really, by graphing them, help you draw the actual curve. Okay, moving on. Last but not least, there's something called holes in your graphs. Now, if your factor of x minus b is a factor of the numerator and the denominator, we've had all different definitions as we go along here, but if it's a factor of both, then there's going to be a hole in the graph where that x equals b, or that 0, occurs, unless x equals b is a vertical asymptote. Then there won't be that hole. So it first says identify all asymptotes and holes in the graphs. So going back to our process, let's do our vertical asymptote, horizontal asymptote, and then holes. So make a little chart so we can just sort of keep track of our answers. And again, doing them in order, we're looking for factors of the denominator that are not factors of the numerator. Now we got a problem on this one, a couple of reasons. It's not factored, so job 1, factor it. And the second thing is the numerator is all random, so we need to organize it a little. So let's go and do the denominator maybe first because it's ready to go. What multiplies to give me 35, that adds to give me 12. I think most of you can see that one. It's 7 and 5. On top, rearranging it, keeping the signs with them. What multiplies to give me -28, that adds to give me +3. So we got x and x, 28, so that should be a +7 and a -4. Okay, so look at our combinations there. Now our definition again, and this is what you got to do, work on your definitions. Vertical asymptotes factor the denominator, but not the numerator. So the x plus 7 is a factor in both, so we can't take that. The x plus 5 would be our 0. So we want to say x equals -5 would be our vertical asymptote. Okay, horizontal, we're looking at our p and q's, and it looks like they have the same degree. So we want to go back to our coefficients. So look at your leading coefficients. And on this one, y equals our numerator's coefficient is a 1. Our denominator's coefficient is also a 1. So we get y equals 1 as our horizontal asymptote. And then last but not least, by definition of our whole here, if x minus b is a factor of both, and we do have x plus 7 being a factor of both, but it says when there is a hole in the graph when x equals b, unless x equals b is a vertical asymptote. So we should be getting, it's a factor of both, and the -7 is a vertical asymptote. So the question is, do we have a hole or do we have no holes? We do have a hole at x equals -7. Okay, so we listed our asymptotes, we're horizontal, and then based on the definition, our hole should say x equals -7. Okay. And again, why was x equals b? Because that repeating did not repeat in the vertical. That -7 was not part of our vertical asymptote. Okay, with those 3 new definitions, how to find vertical asymptotes, horizontal asymptotes, and holes of our graphs, you're going to be asked to jot some down. You're going to be asked to do a few graphs as well. But I think you will be good to go. And again, you're still getting more work on your factoring skills, which is definitely a good thing. So bring any questions you have to class.